And as others, this is a really new talk, so I would like to apologize for all the mistakes that are inside. And please ask questions whether you want when you don't understand some stuff. So my purpose will be to, this is awful, will be to explain how we can investigate self-similar sets, which are called Rauzy fractals, by using new tools, which are very combinatorial and made of discrete planes and two-dimensional placement rules. So it will be somehow technical, and so please interrupt me. And I would like to start with some philosophy in some sense, which is what is repetitivity? If you look at many mathematical objects, which are somehow dynamics, you will find repetitivity in many different shapes. I mean that if you go to topology, then you can say that a compact set is self-similar if it can be decomposed into shrink copy of itself. So this is my favorite. Where is it? Yes, this is my favorite compact set, the Rauzy fractal. But if you switch to physics, then you have this notion of quasi-crystals, which is also fixed by a decomposition process. And if you switch to dynamics, then you have self-induced maps. So this is the addition of the golden ratio modulo 1. And if you look at the induction process over the large interval, then you obtain exactly the same shape. Okay? So this is why we say that it is self-induced. And if you go to number theory, and when you say that phi squared equals phi plus 1, in some sense it is also repetitive because you can recompose phi squared by using the initial steps. Okay? And then finally, if you go to combinatorics, you also have repetitive words, such that the Fibonacci word 1, 2, 1, 1, 2, 1, 2, because you can recode it and obtain some stuff which is exactly the same. So I made a mistake here, I'm sorry, but you imagine that we are, no, it's okay, that we have the Fibonacci word. Okay? So the main purpose is to say, okay, we have all these repetitive stuffs in many domains, and actually they are considered with a quite similar scheme. So we have a very general scheme which says that if we have a repetitive object, then we can see it in a combinatorial way. So we can switch from this repetitive object to combinatorics, just as a Fibonacci substitution. And if we have this combinatorics object, substitution, then we can construct a self-similar set, which is my Rauzy fractal or central type, depends on the domain where you live in. And actually, the main idea is to say that the properties of the initial set, the repetitive object, might be understood better by looking at the fractal set. Okay? And this is a very large strategy, in some sense. So it has been applied in many domains, just as told before. When you go to physics, with using this strategy, you obtain explicit cut and product schemes. If you switch to dynamics, you can study tiling space with pure discrete spectrum or invariant for tiling space, just as Lorenzo did. You could also breed Markov partitions. So it's always with the same spirit to say I want to look for self-similarity, and I switch to geometrical, to Rauzy fractal and geometrical and fractal topology. And if you are in combinatorics, then you can look at free group automorphisms, which are also substitutive. And these topological, these fractals provides you transversal dynamics for these automorphisms. So we can have more information. And also in number theory, so we have many works from Akiyama and many people who are dealing with induction process to understand best simultaneous approximations, expansions, with the expansion with several bases, and also even some proofs for irrationality. So it is, what I want to say is that it is always the same stuff. We are using this self-similar combinatorial process, translated into a fractal, and then to study the fractal. So this is the main, since it is a new talk, I try to make many steps so that you understand exactly what I want. I try to understand what I want to say, actually. So what I want to say is that self-similar mathematical objects are related to topological properties of fractals. This has been seen in many papers. And then the problem is that when we are looking and investigating the topological properties of fractals, then we are very limited by algorithmic features. So this is what I want to explain now. Because if you want to investigate all these domains and all these fractals, actually you always do the same thing. You build a graph to describe the self-induction process. This is what we do. So first we have a dynamics, we have a zoom over the dynamics, which is a self-induction process, and we record the places of the new tiles with respect to the previous structure. And this provides a finite graph, saying where we go. In some sense, we just track where we go when we apply the dynamics. And then what we are looking for, we construct some graphs, and then we look at the property. We reduce the graph with ergodic or number theoretic properties. And this allows to study the initial properties we are looking for. So also, this is a very general scheme, and I could speak 2 hours on that, but I will not focus. But what I want to stress out is that this scheme has been applied everywhere. If you look at Lee's condition and also at Chiavelli, then you have this algebraic condition, we have this strong overlap condition in tiling space, we have geometric coincidence condition in substitutive space, we have the super coincidence conditions, the boundary graph conditions, and the W property. So this is listed. It is always related. It is related to very specific stuff. I mean, this is for beta numeration. This is for tiling space. This is for quasi-crystals. This is for more discrete planes. But when you look at that from abroad, actually you find exactly the same process. And actually, they are all the same. This is, I would say, the limitation of all this is that when you want to study and to look at the differences between all these conditions, they are very, very close. There are very few differences. And this brings us to a limitation, which is that all building this graph and studying their properties is mostly algorithmic, which implies that we have very few general properties of the object we are studying. So for instance, the Piso conjecture that was mentioned by Akiyama is experimented on each substitution and not on families of substitution. And the reason for that is that we are building graphs algorithmically and then studying steps for each example different, independently. Okay? And then if we want, when you first you read this graph and then you connect to the domain you came from, and then you investigate usually many questions. So what is interesting here, so I listed some questions in several domains, and actually when you want to investigate this question, you connect them to fractal topology. This is what is done. If you want to understand who has a finite expansion, then you look for inner points in fractal. If you want to understand, if you want to find for Markov partition, then you look for connectivity. If you are looking for matching rules, then you need to have simple connectivity. It depends on the domain what you are using, but it's always the same scheme. I start from a self-similar mathematical object. I encode the self-similar process into a graph, and then I understand. I encode into a substitution which gives me a fractal, and I also encode the self-similar process into a graph, and I make the relation between the fractal topology and the graph, and the first initial question. Okay, so this may be unclear, but what I want you to remind is that finally, starting from very generic question, we come back to topological properties of fractals. And this is where we are not happy, because when you look at such fractals, the topological properties are very, very intricate in some sense. So the first fractal that was built that way was a Rauzy fractal. It's a very, very nice potato, and everybody likes it. But if you this one is quite nice as well. If you switch to that one, it's not nice. It's disconnected. It seems to be disconnected. Okay. You switch to that one. This one is awful because it seems to be not too bad potato, but actually it's not simply connected because we have islands just through there. The limit process reconnects this part to that one. Okay. And also for this one, this is 0, and actually it's on an inner point. It's on the boundary because we have also an ISMA that comes here. Okay? And this one, the same for that one. This one, 0, is not an inner point because we have many connections inside. So what I would like you to remind of is that actually we can start from many general questions related to self-similarity. We arrive to topological properties of fractals. This can be translated. And these topological properties of fractals are not easy to understand. And the problem is that the only way to understand them is to capture these properties is based on these graphs I told you about. And so it's purely algorithmic. It's purely, I'm very proud to have some results. I mean, proving that this is not dislike is very exciting. But for sure, I'm not able with such graphs to prove that a family of fractals is dislike. Because I need to compute the graph, to study the properties of the graph, and then to obtain some conclusions. So we have a question. So, yes, this is the green part. Conclusion of this part. Investigating the Piso conjecture, fractal topology, and so on, is very limited by algorithmic features. This is the point. And what I would like to focus on is to present a new techniques to try to overcome these algorithmic features. And actually, the idea is not to rely on these graphs and focus, which describes the zooming on fractals, but to rely on the generation process of fractals, which is much more general and allows to investigate general properties. So this leads us to discrete planes. And before defining discrete planes, I want to make some philosophy. I mean that the problem with the limitation that I mentioned before is that we are zooming on the fractal and trying to describe, so maybe I shall come back. In order to understand these properties, we need to zoom in the fractal and to describe all the intersections between points. So we have this zooming process. Look at the boundary, describe very precisely the boundary, and understand what happens. And this is a real limitation. So the idea to overcome this limitation is to say, no, I'm not going to zoom in, I'm going to zoom out, just to look at the general properties. And this requires to introduce so we have to stop zooming in. We have to stop look at very small, teeny things, and to look at this in a very general process. And for this, we have to investigate the properties of discrete plane. So what is a discrete plane? Nice picture. So Timo Jolivet did it. Actually, if you are in R3, a discrete plane is nothing but the boundary of a plane, a discrete boundary of a plane, which means that you consider a plane in R3, you just put it, cover it with faces of cube, okay, and you keep just the boundary of these faces of cube. Is it okay for everybody? So the formal definition is to say that it is a boundary of the union of unique cubes which have a non-empty intersections with the lower half space, the half space which is lower the plane. Is it okay? So this is a discrete plane. And actually, these discrete planes are very interesting. This is why I want to focus on them, because they are actually the ones that that model the position of atoms in self-similar tilings. They also provide examples of two-dimensional sequences with low complexity. And also the feeling is that they are very related to continued fraction algorithms or to this fusion process from Natalie. Actually, it's something, I think they are very connected. the SID conjecture from Valérie this afternoon. So my purpose is to say we have these discrete planes, but we don't know them enough to exploit them, to take benefit of them. And we should do that in the future because they are a good model which is not enough investigated. So, and the main fun question, but we have to start from the beginning because we don't know many things about them actually. So we come back, and the question is how can we generate these discrete planes? We have this very general definition, but it's not enough. And for instance, what a process that has been enhanced by Arnaud and Ito is to do this. So look at this, we start from that, and then I add a piece, and I add another one, and another one, and another one, and another one, and so on, until I cover the full space. And what I want to describe is how we get to this process. Okay? And actually, what we were doing, actually, when I come back, is just a substitution process. So I replace some faces of cube by other faces of cube with a very strict, very defined process. So I will tell you more about that. And so the question will be to understand what are the substitution rules, so these new substitution on faces of cube, and then how to generalize them. So, okay, so we are in the grid part. I have told you that the family of discrete planes is strongly connected to the Piso conjecture. And now what I want to focus on is these substitutions stuff. And to have this substitution, we need to go into more technical stuff, which is that the base, if you want to work with discrete plane, we need to describe what are these elementary units, the faces of cubes, okay? So how do we describe them? We describe them with a position. So we consider faces of cube, and they have a position, which is a vector, three-dimensional vector, okay? And then they have a label. So this one, which is 0, 0, 0, 1 star. Star means we consider a face of a cube. 0, 0, 0 means that we are just placing the cube at 0, 0, 0. And 1 means that we consider the cube which is orthogonal to the E1 direction. Okay? And for that one, so I go to 0, minus 1, 1. I put a cube and I look the face which is orthogonal to the E2 direction. Okay? So my discrete plane, instead of, you can look at faces of cube, but if you want to formalize that, we use this concept of tip, which is some pairs of vector plus a position, plus a label. Okay? And then what we have to do is to define actions, substitutions over the steps. I want to act on my discrete planes. So to do this I will base the construction of my two-dimensional action on a one-dimensional action. So I start from a substitution, which is a one-dimensional process. So I think everybody knows it here. So for instance, the Fibonacci substitution, that we should know. 1 goes to 1, 2, Fibonacci, sorry, 2 goes to 1, 3, and 3 goes to 1. And then what I will do is to build, to give you this very nice formula. So you should not like it. It was exhibited by Arnaud and Ito. Many people have many difficulties to understand it, but actually it's basically, it's obtained by duality, in some sense. And what does it represent? It represents somehow the self-similar process. So I will not go more into that, but you have to say, okay, this is a formula, it's not nice, and you can apply it, so now it becomes nicer. You perform the computations here, and what you obtain is this. So my formula says, okay, I have a substitution, and I can provide some two-dimensional rules. Forget about the details. For instance, what I say is that this face of cube will go to a full cube. This face will go to the first one. And this one, the horizontal one, will go to the second one. Okay? The formula, please don't take care of the formula. Why do we focus on this, such a construction? Because it is because we have very nice properties. I mean, like these rules have very strong properties. So first, they are linear in some sense, because when we apply the substitution, the generalized substitution to a tip, to a vector placed in X, what we do is to apply it on 0, so the initial center, and then translate it by n minus 1 of x. So it's, I said linear, it's not linear, but we have a linear connections. Okay? And also what is much more important is this property. Thanks to the formula that I gave you, if I consider two faces on a discrete plane and I compute their image, then if the faces are distinct, then the images will not overlap. So the main interest of this formula is to say, to ensure that everything will be disjoint. I start from two disjoint stuff, I will obtain two disjoint patterns. Okay? And I think I have examples. So these are many examples of computations. We have, this is the one I showed you, but this is another generalized substitution, and another one, and another one. All of them are obtained with different sigma, substitution sigma, and they all share the same property. When you compute the image of two distinct tips, faces of cube, you obtain completely disjoint patterns. So this defines, this allows us to define something, a map on a discrete plane, because it will be, there will be no overlap. And what are they useful to? Actually, they are useful because they provide an action onto the family of discrete planes. I mean that if you compute, you start from a discrete plane, you apply this substitution process, what you will obtain is another discrete plane. So we start from the plane which is orthogonal to a vector V. What we obtain is a plane which is orthogonal to the vector transpose of the matrix V. So we have an action over this family, and this is why this is related to this fusion process, because we can play with the full family and discrete plane and switch from one to the other. Okay? So the idea is to use this formula, this switching formula, to build discrete planes step by step. And how do? We fix an initial vector that we want to understand. So we fix a discrete plane that we want to build, and we expand the vector with a continued fraction algorithm. Anyone you want, and we have many possibilities. So this means that we write a vector as m1, mn of vn, and the matrix m1 and mn have integers entries, and usually we choose them in a finite family. So we can consider continued fraction, Euclid, and so on. We obtain a decomposition. And then to each matrix, we associate a substitution, an appropriate substitution, which has a good matrix. And we replace the matrix by this generalized substitution. So what we obtain, we start from the unit cube, and we apply the first substitution corresponding to the first matrix, and the second, and the third, and so on. And what is really nice is that by doing this, we build increasing pieces of the discrete plane we are looking for, just by looking at these pieces. So I apply my process, and I start from this. Then I have a first substitution corresponding to m1, and I obtain this, and then a second, I obtain this, and so on and so on. All these pieces are part of the discrete plane I want to build. So it means that I have a process when I used my when I decompose a vector to reconstruct step by step a discrete plane for any vector. Okay? But this is very dependent on the choice of the substitutions. I always obtain a piece of my discrete plane, but it depends, the shape I will obtain and the pieces I will obtain are dependent on the choice of substitutions. And actually there are many possible choices. So you can use a Jacobi-Perron algorithm, which is the example before, and you expand, which is a generalization of the continued fraction algorithm. Then you have some families of substitution, and we obtain such stuff. I can also use our Rauzy substitutions, which are related to a sequence of complexity 2n plus 1. So these are the three substitutions, and I obtain such stuff. Okay? So they are not the same. I do not build the same discrete plane, but I obtain some stuff. We can also use elementary substitution in order to expand Sturmian substitution, and we obtain not nice pictures, such as this one. Okay? So we have a very nice features. And so we have this discrete plane. We can define this action, this substitution over the discrete planes. And actually, what I would like to explain is that it is somehow limited again, because computing this iteration is very bad. So the next step is to replace these substitutions, these awful formulas, by simple stuff. And how do we do that? Actually, or maybe the philosophy behind, is to say that I want to select the good substitution to construct my discrete planes. And the good criteria, in some sense, is to look for nice shapes. I mean, what we want to do is to select the good substitution to have connected patterns or with nice increasing radius and so on. So to do that, we need to understand more the connectivity properties of the patterns. And this is a very difficult question. So now I will focus in a sub-question of this question, which is that we are going to apply always the same process, the same decomposition. And for instance, if you look at this one, sorry, where is it? Yeah. If you look at this one, we obtain these patterns. If you look at this one, we obtain these patterns. Okay? And if you apply always the same patterns, actually, what do we get? We get a Rauzy fractal. We get the pictures we had before. So why do I mention this? Because if I want to have, finally, if I want to have good patterns here, it means that we need to have good Rauzy fractals in some sense. Everything is connected, that I told you before. But, so for instance, look at that. We had this stuff, and I renormalize it, and I project it onto a good plane. This is what I obtain. And you look at this, renormalization and projection, and again, and again, and again, and again. What you see appearing is a Rauzy fractal. So there should be a color here. Sorry. It's better on my slide. Okay? So what does that mean? I mean that if we want to investigate the shape of, where is it? Do you see? There, here. The shape of these patterns is the same as investigating the shape of the limit shape here, in some sense. How do we do that? So we need to check this connectivity of such patterns. And the main process is to have a better understanding of the positioning of rules. So I have told you about these substitution rules over, I replace a face of a cube by another face of a cube. This is not nice, because I have to compute the position, this n-1 of x all the time. So what I want to do, is to say, okay, I have my images, but I don't want to compute the next image. So I want to focus on positions. For instance, if you compute the image under a substitution, by dimensional substitution, the image of UV is going to be the concatenation of the image of U and the image of B. You never compute the rest. We want to do the same here. So we know that this piece, okay, goes to that shape. We know that this piece goes to that shape. The question is, where does the image, what is the position of the images? So for instance, so what we say is that we can compute this stuff. This shape goes here, and I will put the image of the white one at the down left side of this one. I can compute these positions. So you seem all to be lost. Who is following what I'm saying? So what I want to say is that actually starting from all this process and all these very strict, awful formulas allow us to compute exactly what are the positions of the pieces. And finally, we have a nice setting to play with discrete planes. So because we have a discrete plane, we can act over a discrete plane with something which is very close to a one-dimensional substitution. So how do I use that, for instance? I want to compute the image of that one, okay? So I start, where is it? Oh, you don't see the color, okay? So I start with this one. I put this image, and then, okay, so it doesn't work. And then I compute the rest. There should be color somewhere. So you have to believe me, but yes, okay. I have some problem with my colors. Okay, starting again. I start with that one, so this should be this one. Then I will use this piece, and I know my local rule. Then I will apply and add a piece. Then I will know this piece, and I will add a piece. Then I will know that one, and I will add a piece. And I know that, and so on. Okay? So this allows me to compute, step by step, the images of the pieces. And this allows me, eventually, to build Rauzy fractal by going step by step with these concatenation rules. I don't have to use anymore any formula with matrices. I just use these concatenation substitutions. And so I started with the question, how can we describe a discrete plane? And now the answer is, okay, we have a very combinatorial viewpoint, which is positioning process. And what is the application? Actually, the application is that we can study connectivity of families of fractals. Because these are my local rules, my positioning rules. And actually, if I start from the unit cube, I never need that one. I can cover any of my pieces without using, this piece. When I start from the unit cube, I never need to use this part of the question, of the local rules. And what you see is that when I apply these rules, they are all connected. So when I start from something which is connected, I will switch to something which is connected, and again and again. So this allows me to prove that all the final process is connected. It's very simple in some sense. If you have nice rules, then you obtain connectivity. So the idea is to say, okay, I have this concept of stable set of placement rules. I start with rule, and what I want is to cover any part of my patch, of my pattern with with a path of intersecting connected rules. And if I have that, if this is stable, then, so let us switch this, it is a proof, but actually, if it is stable, then the connectivity is maintained from step to step. This is the idea, okay? And I obtained some very large criteria for connectivity of renormalized limit sets. So for instance, we can prove that the smallest piezo number substitution is connected, and every Jacobi-Perron substitution also is connected by using these rules. But this was already known. The main interesting point is when you switch to families. Because if I want to understand whether our Rauzy substitutions are all connected, which is that I have these three basis substitutions, I compose them all together, I obtain a new substitution, and I want to know whether the Rauzy fractal corresponding Rauzy fractal is connected. This was a conjecture by Canterini. And how do I do that? I compute my placement rules. Okay? But that's not time because they are not nicely connected. This point is not nice, it may create some problems. So I have to refine the rules and to change them. So this is a technical point. Instead of using this pattern, I will use larger patterns which gives connectivity again. And then I have stable set of rules and I can apply my machinery. And the interesting is that I can play with these rules in any order. So we have this fusion process. I take one rule, then another one, then I come back to the first one, then to the second one and the first one. Everything works together. Everything matches. And by the end, what I obtain is that actually everything, applying any Arnoux-Rauzy substitution to the unit cube, gives me a connected pieces and associated connected fractal. It works. So this gives us a very general result, which is that for all our Rauzy substitution, the fractal is connected, which was not known. So it doesn't work. It works for Jacobi-Perron substitution, but it doesn't work all the time. We have to be very precise with this connectivity stuff, the placement rule, because for instance, here we have for the elementary substitution, we do not have connected pieces. So this means that we have a strong need for a good choice of continuous fraction algorithms and substitutions. But as a result, yes, what I want to stress out is that these placement rules, which are may not like combinatorial object, allows investigating topological properties of large families of fractals. So this may seem quite anecdotal, but actually for me it's just one step into a very general process. Because thanks to that, we have now a tool that may allow us to investigate, for instance, the Piso conjectures. Proving that some substitutions, a family of substitutions satisfies the Piso conjecture relies or is equivalent to prove that we can build discrete planes with patterns with an increasing radius. It's exactly the same. We have to have increasing pieces and pieces. So since now we have these tools, these two-dimensional substitution, these placement rules, we can look and try to investigate the radius and obtain and investigate the Piso conjecture for all our Rauzy substitutions, for instance, or maybe a subset. So this is something that we would like to investigate in the future. And also, more generally, I think that all this, at the moment we can generate connected pieces for any discrete plane, but so this can be used to investigate more the family of discrete plane as a SID conjecture process or a fusion process. We can act from one discrete plane to another one and exactly understand how it goes from one side to the other side. We have a good setting, a good framework to do that. So this allows us may allow people to propose some good examples for branch manifolds, for fusion process, SID, or even to generalize this concept of Rauzy fractals for non-algebraic vectors. Everything can be done, many things can be done now since we have the good framework to play with. I'm sorry for those who were lost, and thank you very much.